Dr. Moses here. This experiment is recrystallization, recrystallization. That means something was pure and became impure, and we can make it pure by growing crystals, so crystallization. So in this experiment, actually, you're going to use benzoic acid. Okay, so benzoic acid is supposed to be a clear crystalline compound, but what we've done on here, we've already made it impure by adding carbon black or activated charcoal. We've added carbon. So instead of this benzoic acid being clear and pure, it's going to be grayish. So it's going to be grayish. We need to purify it by crystallization. We're going to use H2O. Okay, so we're going to use water, and in this case we're going to take advantage of hot water. Carbon does not dissolve in hot water. Benzoic acid dissolves in hot water but not cold water. That's why we're using water, and also water can be removed when the process is done. We're going to do two types of filtration. So there's gravity filtration, and we'll also do vacuum filtration. All right, so let's dive in. So there are other methods of purifying organic compounds in the lab, including sublimation. For sublimation, this is usually used for compounds that sublime. To sublime is when a compound or a substance or matter changes from solid to gas phase without going through liquid phase. So you never go through liquid. Okay, you never go through liquid. It's directly changing from solid to gas phase. And of course, an example for this is going to be dry ice. So if dry ice is mixed with, say, carbon does not sublime, so you would just let the dry ice sublime off and collect it on a cooler surface, say like a watch glass which has cold water. You'll have the dry ice subliming, a block of dry ice subliming onto the cooler surface, and you would collect it out of there by scraping it off. Okay, same thing happens with iodine. All right, iodine is also another compound that can be purified by sublimation. It forms purple vapors. Extraction will be done in experiment 3. Okay, so we'll do this in experiment 3. We'll never do sublimation for this lab. Chromatography is done in another class, but it's one way of separating compounds, organic compounds. And then distillation, I think we're gonna do distillation in experiment 4 and 5. We're going to separate two liquids that are volatile by distillation based on boiling point to do that. Okay, so today we're doing recrystallization, purifying benzoic acid to make it pure. So what's a pure compound? That's a homogeneous sample containing only molecules of the same structure. Of course, homo tends to mean same or uniform. Genus comes from the word genera. Of course, genera, you'll know that means type, I think, in Greek. So same type of molecules in one substance. So you want it to be pure. You want it to have the same substance in a sample. In this case, benzoic acid will be purified. And once it's pure, we would have let it dry, and then we'll check and assess for purity using melting point. So melting point is a physical property that we can take advantage of to check for purity. If it's pure, the melting point usually has a narrow melting point range, and it's going to be a sharp melting point range. But if it's impure, the melting point range found from the experiment is going to be lower than quoted in literature or online. Okay, so that will be for experiment 2. So the narrow melting point is a characteristic of a pure compound when the melting point found is narrow. So that's it. If it's widened, if the range is widened, then it means the compound is impure. So how will we do this? We're going to take our impure solid. We'll take our impure solid, which is a mixture of benzoic acid and carbon. When I started, I told you it's going to look grayish. We'll take our mixture and dissolve it in a solvent. Not too much solvent. We're going to use just a little solvent. Why do we need a little solvent? Because we want the solution to be saturated. Saturated means full of, saturated. So you'll take your sample and drop it into an LML flask, and this experiment is going to be demonstrated by me because of time, okay, in the mixed class. So we'll take a sample and then drop it into an LML flask. So that's the benzoic acid with the carbon in the LML flask, and then we'll be adding a portion of 10 ml of water, okay, followed by, I think, 1.5 ml portions or 2 ml portions into the flask. So we'll add while heating on a hot plate. Remember, I told you we're using H2O because benzoic acid only dissolves in hot water, and carbon never dissolves in cold or hot water. That's why we're using H2O. It's a good solvent for that. We'll talk about it later. So you heat. We'll heat it to make sure that the mixture of benzoic acid dissolves, while the carbon particles will be floating around as black specks. And then once it's all clear and not cloudy, we'll stop adding the water and we'll stop heating, and then we will do gravity filtration and cool it after gravity filtration and filter out the crystals that will have been formed. So we need a saturated solution in the flask. We don't want too much solvent in there. Alright, so why do we choose H2O? H2O has a favorable temperature coefficient. What does that mean? It means one of the components in our sample will only be soluble in hot water or hot solvent at high temperatures. And the carbon, as I said, which is one of the solids in the mixture, will always be insoluble in whether cold or hot solvent. So the solvent of choice should have a favorable temperature coefficient, which means it should dissolve one of the components when hot and not when cold, and should never dissolve the other component of the mixture to be separated whether hot or cold. So that's the first step, first criteria of choosing a solvent to use for recrystallization. The second one, of course, ties with number one. The impurities will be insoluble in the hot water or cold water, so you can filter them out. And then the third one, the boiling point of the solvent, which in this case is H2O. The boiling point of the solvent should be lower than the melting point of the solute. The solute is the solid you're dissolving in the solvent. Solute plus solvent, remember, equals to solution. Solute plus solvent gives you a solution. The solution could be dilute or saturated. Okay, so H2O, boiling point of H2O is 100. Alright, melting point of benzoic acid should be around 122 degrees Celsius. So water qualifies for criteria number 3 because water has a lower boiling point compared to the melting point of our sample of interest, which is benzoic acid. Okay, melting point of benzoic acid is 122. Alright, why do we need it to be low enough? It needs to be low enough so it can easily be removed from the crystals after you form your crystals by filtration or evaporation. That's why we need the boiling point to be low enough. That's a very important point. Okay, the solvent should not react with the material to be separated. That's another criteria. In other words, the solvent must be inert. Should not change the chemical property of sample being purified. Okay, sometimes to recrystallize, you might need a mixture. Remember, today we're only using H2O, or in this experiment, we are only using H2O. Sometimes you might need a mixture. For example, sometimes you might need to mix some H2O with some ethanol to get the right temperature coefficients. Okay, but today we don't need to do that. Okay. The process, like I said, involves you weighing the solid. So you weigh the solid and drop it into an LMR flask. Okay, so that's your solid dropped into your LMR flask. And then you add some boiling stones. The reason why we need the boiling stones on here is to control rate of boiling. Like, you don't want the liquid to be bumping out of the flask. Okay, so you want it to be controlled. You know, whenever you're heating a liquid, for example in a pan, the surface jumps up and down. So that's without boiling stones. But with boiling stones, it will really be calm on the surface. You're boiling, it's boiling, but because of the boiling stones, the surface will not be crazy, will not go crazy, will not be bumping out of the container. Okay, so that's why you need boiling stones, for safety, to control or to help even heating of the liquid and control the rate of bumping of the drops or the bubbles out of the liquid out of the container used to heat the liquid. So we're going to add a few ml of the solvent and heat to boiling. So we'll add a few ml of the solvent. Remember, we said we want it to be saturated. That's why we are adding a few ml of the solvent, so that the solution stays more than concentrated, which means it stays saturated. So we'll add small amounts of solvents as need be to make sure that all the cloudiness is gone, and that means all the benzoic acid will have dissolved. The cloudiness that we will see will be because of undissolved benzoic acid, so we don't want to see that. That's why we'll keep adding small portions of the solvent, keeping in mind we want the overall solution to be saturated. So meanwhile we will be heating our sample, all right, on a hot plate. The sample will be sitting on a hot plate and heating it. We want to keep it hot so that the benzoic acid will dissolve. Okay, and then as the benzoic acid is dissolved, we're going to filter the solution while hot by gravity filtration. Okay, by gravity filtration. So the heating just helps to dissolve the sample. We call that process dissolution. Okay. If too much solvent is lost because of filtration, we'll add some more, 2 to 5% if need be, to make sure that the solution is hot and well solvated. Okay, so for gravity filtration, when your sample is hot and everything is dissolved, we're going to use a fluted filter paper. Picture folding a filter paper into half, so probably you'll end up with 2 leaflets like that, and then fold it one more. You're going to end up with 4 folds like that, and fold it one more time. You're going to end up with 8 folds of some sort and a very tiny cone. Open it back up to the 4 folds, and then you open it up. We will end up with a creased fluted filter paper that looks like this. So those creases are very important, and these are questions that I always tend to ask. These creases help the solution to flow. See what during gravity filtration, we'll be pouring a hot solution into the filter paper, right? Okay, so the creases will help the solution to go right down to the bottom of the filter paper. The filter paper is going to be supported by a broken glass funnel, which will be sitting on a beaker. All right. So the broken glass funnel is going to be of this shape. So that's your glass funnel. It doesn't have a stem. It's broken there. You know, normally for a funnel you do have a stem. We intentionally broke out this part took off that part, so we have a broken stemless glass funnel. You should have it as one of the figures in your notebook. Stemless glass funnel. Alright, so your filter paper will sit on the stemless glass funnel, and I told you it's creased to increase the surface area for water flow, for solution flow. You want the solution, as you pour it, you want it to quickly go down there, because if it delays, you're going to have premature cooling of benzoic acid. I told you benzoic acid does not dissolve in cold water, so you want to keep it as hot as possible, So once you pour it, it's gonna drain down into a collecting beaker, right? Collecting beaker, so it will drain down. In fact, you should be seeing some crystals forming already. If you used the stemmed funnel, that will be wrong. Why is that not recommended? If you use the stem funnel, you're going to get clogging. When you pour your benzoic acid in here, remember this stem is cold. So because the stem is cold, your benzoic acid solution will cool on this part and prematurely cool and form crystals and clog the funnel, and nothing will pass through. That's why we don't want to use a stemmed funnel. You have to use a stemless glass funnel. Stemless glass funnel. Okay? Stemless, you don't want the stem on there. That's the main reason. Now, as filtration continues, on the filter paper, you're going to see black specks. Those black specks are carbon. So the material that is trapped on the filter paper, the general term for those particles that are found on the filter paper, those are called residues. Okay, and the liquid that passes through the funnel, the liquid that will be dripping down, is called a filtrate. So the residue on the filter paper will be the carbon and any sand particles, any sand insoluble impurities. Okay, so the carbon is insoluble, any sand impurities. Let me write it down so you know what I'm talking about. The sand impurities will also be trapped in there. The carbon residue will also be trapped in there. Those are insoluble. Now in the filtrate, you're going to have three things. You're going to have benzoic acid. Alright, you'll have benzoic acid. That's one. Number two, you're going to have soluble impurities. Number two, you're going to have soluble impurities. Okay, and then number three, in there you have H2O itself. What are the soluble impurities? Soluble impurities might include other sugars. You know, sugars are soluble in hot or cold water, and also could include color. But I don't expect color to be there. Why? The very first reason where we mixed benzoic acid with activated carbon, which is just activated charcoal, is to remove color. The activated carbon removes color. It's an impurity in itself, but it also removes color impurities. So I don't expect the color impurities to still be in there unless you mess up somewhere in the experiment, but I'm going to do it myself as a demonstration, so we don't care about that. Alright, so assume now the color is gone, the insoluble impurities, which is carbon, sand and carbon, is gone. So now assume we have only benzoic acid in the filtrate, benzoic acid and H2 in the filtrate. So the next step is going to cool it down. We'll cover, okay, so when you're done, we will cover our beaker containing our filtrate, which has only benzoic acid and water. We'll cover it to protect it from airborne impurities and cool it down slowly to room temperature. Ambient temperature is just room temp. room temperature, and that is gonna help the crystals to grow, because remember I told you benzoic acid does not dissolve in cold water, only dissolves in hot water. That's why we heated the solution in the first place. Now, to make sure you have most or all of the crystals formed, we're going to keep the beaker onto an ice bath. So we'll bring ice bath to the lab and stick our beaker in there so that it can chill to form more crystals. So when it's cool enough, you'll feel it by hand, by your hand palm. You'll see lots and lots and lots of needles in floating in the water, and then that's when you are ready for vacuum filtration. Vacuum filtration is going to be different from gravity filtration, because we're going to use suction to create a vacuum. Okay, now you don't want to cool it too fast, too quickly. You just don't want to take your hot beaker. You don't want to take your hot beaker right here and place it on ice. You have to at least get it to room temperature before you put it on ice, stick it on ice. If you do that, if you cool it quickly, then you're going to get very small crystals, which increase the surface area and retain impurities. Or you could get big crystals which formed quickly, which occlude solvent and impurities within themselves. Whenever you have a very big crystals, the impurities might hide within it because you rushed the process. That's why we want to cool it slowly to room temperature before putting the flask on ice bath. Now that you are ready to vacuum filtrate to remove our beautiful crystals, we will need a filter paper and a Buchner funnel and a thick-walled MR flask. So the funnel that we're going to use is special. It has holes on it to let the water drip through, and we're going to drop a fitting filter paper. That filter paper has to be weighed, pre-weighed. Why? Because after we filter and get our crystals, we'll keep the crystals to dry, and then we'll weigh the filter paper plus the dry crystals to determine our percentage recovery of pure substance. So the filter paper must fit in the funnel. We will have to wet it. This Buchner funnel, the spelling for Buchner is that. The Buchner funnel is supported onto a stopper which is on the neck of the thick-walled flask, something like that. So the thick-walled flask has a vent. The vent is connected to a tubing, and that goes to the vacuum. Okay, so the vacuum will be sucking out air from within the flask, creating a vacuum here. The vacuum suction or the vacuum pump will be sucking out air from the flask, creating vacuum inside here, and that will cause the liquid to drip down during vacuum filtration. Alright, so the setup will be like this. So you'll be pouring your liquid containing your crystals onto the filter paper, and it will drain down here. So whatever is draining down here is H2O plus soluble impurities. Okay, and then your crystals will be collecting up here, and then we'll lift it. Once it's done, we'll rinse the crystals, and then we'll lift it up with a spatula. So you will have your filter paper carrying the crystals. We'll keep them out for a week to dry, and then we'll weigh the percentage recovery. So we transfer, like I said, the crystals and the filter paper onto a watch glass or a weighing boat, cover them and keep them to dry in the safe location. After we weigh them, after they dry, we'll weigh them, and because we pre-weighed the filter paper before, we're going to subtract the mass of filter paper, and we're going to subtract the mass of the filter paper only from the combination of the filter paper and the crystals, and then get the percentage recovery. So this is what I'm talking about. So suppose mass of filter paper only is about, say, 0.2 grams, and then mass of filter paper plus dry benzoic acid, and the mass of filter paper plus dry benzoic acid is, say, 1 gram. Okay, and suppose that the original mass here is 1.5. So the way to calculate the percentage recovery, we have to find the mass of benzoic acid, which is gonna be just the subtraction, 1 minus 0.2 divided by 1.5. Everything is gonna be multiplied by 100. Okay, so it's going to be 0.8 divided by 1.5 times 100, and of course you're going to get your percentage right there. So this is just an example of how you can calculate the percentage recovery, and you have to do that in your notebooks. So that's how you purify benzoic acid from its impurities. In this case, the impurities are probably sand and carbon. Those two are insoluble impurities. And you also have soluble impurities, which will include sugars and colors. The proof that you have pure sample, you should see the appearance of the substance. The pure benzoic acid should be clear, needle-like crystals, and also the melting point should have been very close to 122 degrees Celsius centigrade. Okay, that's it. Make sure you do your post lab after the demonstration next week. Bye.